Hi, my name is Jeffrey Zhang, and with me I have Philip, Rahul, Sri, Albert, and Mervin. Our 460J group ended up doing visualizing Twitter feeds as our final project. So some background into our final project is that there have been a lot of new advancements made in the field of generative art recently. We kind of wanted to try out exploring this concept and use this to create images to represent tweets. However, we didn't want to just pass in the entire tweet as an input into some text-based kind of pre-built model. We wanted to focus more on generating vivid and emotional images that really captured the essence of the tweet. This kind of was inspired by the fact that frequently in art, you can see depictions of the same kind of subjects, such as two figures in the rain that you can see here on the right. However, by infusing a more emotive aspect, you really understand more of the essence of the image. And so that's really what we wanted to focus during our project. So the basic pipeline for our project was to take a tweet and then do two things. We wanted to extract the sentiment from it and extract the keywords from it. These two operations were independent of one another. Taking those keywords, we would pass those in using clip plus VQ-GAN to create a starter image. Using that starter image, the keywords and the sentiment analysis, we would then use clip-guided diffusion to edit the starter image and try and infuse those vivid emotions into the image, giving us our final output.
So for the sentiment analysis part of our project, we found a dataset by Figure 8 on Kaggle. The dataset contained 40,000 different elements with the tweets, authors, and indices as the features and 13 different sentiments as the targets. The 13 sentiments included emotions such as anger, enthusiasm, and happiness. For our data preprocessing, we used a lot of libraries from NLTK. We started with common things such as the removal of author and ID columns, and also stop words and null elements. We then removed a lot of irrelevant text in hopes of cleaning up our tweets, as less complex statements would help our models a lot. We removed things such as punctuation, stop words, emojis, and URLs, and also transformed contracted words into their full forms. So words such as we've into we have, and also transforming abbreviations. So words such as ASAP into as soon as possible. A couple of notable things we wanted to mention was that this was one of the only data sets we found with this many emotions, but was on the relatively smaller side and would go on to affect our models. We also wanted to find the origin of how all these sentiments were determined by Figure 8, or what metrics were being used, but the documentation was unfortunately taken down.
Now let's take a look at our sentiment analysis model. In general, we wanted to be able to take in a tweet, clean it, and return a sentiment. The first thing we tried was with the convolutional neural network with limited success. Upon further research, we found that a recurrent neural network, or RNN, was better tiered towards our problem at hand. The RNN is special because of its ability to use context. That is, it can take information that the network sees when performing earlier tasks and use them when performing the current task. The specific RNN that we used was the LSTM, which is a special type of RNN that has much more long-term memory. Information from much earlier can be passed through the entire pipeline of the neural network and be used at any given step. As we can see in the bottom, a traditional neural network will just take an input X, pass it to a node A, and put out an output H. But in a recurrent neural network, we were able to have another output that sends a little bit of information to any given node inside the neural network. Now let's take a look at our accuracy metrics. As we can see, the accuracy and loss for the model shows that there is a little bit of overfitting going on, as there's a large gap between the training and the test accuracy as well as loss. We suspect that this is because of the dataset being heavily skewed towards a couple sentiments and not having as many examples of other sentiments. We were able to treat this a little bit by using GloVe, and on the right you can see that the training and test accuracy and loss were able to get a little closer together. Here are some of our results. Given the tweet, we put our Christmas tree today because we were running out of things to yell at the toddlers not to touch. Our analysis model gave us that it was 50% fun and 25% happy. Another one is a delightful day outside in Harlem. It was able to analyze that as 57% enthusiasm and 34% fun. From this, we can see that it is pretty accurate given the sentiments that we had, but it could be more accurate if we had more detailed sentiments.
Now comes the second step in the pipeline, which was text extraction and summarization. So the reason why we included this step in the first place is that we found that tweets in their full form typically do not generate good outputs for image generation. So at first we tried to address the problem using summarization to condense the tweets. We used various summarization models built with state-of-the-art language transformers such as XLNet, BERT, and GPT-2. We also tried training Google's T5 summarization model using an Amazon review dataset that we found from Kaggle. The idea behind this was to train our summarizer on user-generated content, which we thought would be apt for the tweets that we would eventually pass in. However, we found that summarization is mostly used to condense multi-paragraph articles into a single paragraph and not very suited to summarize a 280-character tweet. We found that when we would pass tweets into these to any of these summarization models, we would just get a blank output, meaning that the input was not large enough to generate a summary from. Instead, we decided to use BERT to find the top and most important keywords in the tweet, where n is equal to 3 or 4, depending on the size of the tweet. The way it worked was by finding the embeddings for all the individual words in the tweet, and also finding the embedding of the tweet as a whole. We then used cosine similarity to find the main keywords of the tweet. With this, we found much better results in our image generation.
For the second part of our image generation, we wanted to take the VQGAN plus clip images that we had, that we made from the keywords, and now infuse sentiments into those pictures. And what we chose was clip-guided diffusion, and diffusion models are a class of likelihood-based models that work by taking a starting image or signal and gradually removing noise. And so we chose this because diffusion models have been shown to recently that they can, in a lot of metrics, compete and even beat GANs. And so we decided to use these. And so what we did at first was we saw that when we looked at just an image, whether it be one of our own or one we found on Google, and we told it to infuse emotion, it would give us a result that it worked, and it was a good picture that gave what we asked, but it wasn't really keeping the identity of the original image. And this is because of the way that the losses worked, the way we had originally been using it. So it originally just had included LPIPs, and without us having trained the hyperparameters and scaled the variables in the loss function correctly, it wasn't really keeping the spirit of the original image whatsoever. And so what we did was we needed to first fix those hyperparameters, and then we added L1 loss. And so by punishing the model for straying too far from the initial image, but also not tightening it up too much so that it's able to change the emotion of the image, we were able to get better results. So as you can see here, the cat at first is not kept at all, but after some changes in the loss functions, we were able to get this dog here that that definitely kept the spirit of the original image while also adding our emotions.
So overall, clip-guided diffusion works well in some cases, but not so well in other cases. For example, some pairs of emotions in starter images result in ambiguous or nonsensical generative art. As shown here on the right, we see our starter image generated from Skip Bayless's tweet about the Detroit Lions. After performing sentiment analysis, we found the top sentiment to be fun, but Clip didn't really understand how to incorporate that into the image, so it just wrote that onto the word, or wrote the word out onto the image. So essentially, the generative art works best on tweets that have more concrete nouns and words that stand out. Adversely, it doesn't perform out well on tweets that are more abstract. The pair of images on the top come from the tweet, "A delightful day outside Harlem," and the extracted keywords are outside, delightful, and Harlem. And the main sentiment was enthusiasm. Using these keywords in the enthusiasm sentiment, the model edited the image to be more colorful and vibrant. The pair of images on the bottom is an example that didn't work out all that well. It comes from our professor's tweet regarding the importance of math in the field of data science. The keywords were more abstract, like algebra, calculus, and math, and the emotion was worry. So the model didn't really have a clear definition as to how to portray the tweet. So it just wrote them out in the original image. And then when editing the image with the sentiment in consideration, the model just made it incomprehensible. So in essence, clip-guided diffusion has viable results only for some tweets. Overall, through our combined efforts on this project, we learned plenty about generative art and sentiment analysis. We hope you enjoyed some of the images we generated, and we thank you for listening to our presentation.